Thanks for that introduction, Joe. I'm really happy to be here and to share this work with you. Um, I've been working on Chairables for many years now. And so today I'm going to talk about kind of the overall arc and a couple of the projects in kind of a little bit of a deeper way along the way of building Chairables and thinking about how to design for accessible user experiences. Before we get into kind of the meat of the talk, I want to give a little bit of background on myself and how we, how we got here. When I think about my research, I tend to think about accessibility and engagement as kind of the two driving factors within HCI. So thinking about how we can support people interacting with devices and interacting with information, communication technologies, especially for wheelchair users in the context of Chairables. But generally speaking, I think of my work thinking about how we can design devices and interfaces that better support people with diverse abilities or the diversity of human ability, kind of thinking very broadly about that. And engagement, just to clarify that, engagement I know can have many meanings depending on the context you're in. And so when I think of engagement, when I talk about engagement, I really focus on this aspect of positive experiences, involvement, and participation in new experiences, rather than necessarily kind of the social media types of engagement or things like that, although those do come into play. And so if we think about, I think we can all agree, when we think of smartphones and mobile devices, these are ubiquitous technologies in our society, especially as we think about how we interact with computing and how we connect with one another. These devices make it possible to connect and change the way that we connect and interact every day. And the capabilities for these types of devices grow and change every day. With the growing popularity of wearable devices, we also see these capabilities kind of moving into smaller form factors and being able to kind of move through and show up in new varieties of spaces and for new applications and to help us achieve different goals. They become even more convenient to the point where they are literally at your fingertips or literally on your body, on your wrist. One area where this kind of unprecedented access to technology has a profound potential to impact people's lives is when we consider about accessibility, we consider how people with disabilities may use these devices and these new form factors, these new possibilities. However, the technologies themselves are far from perfect. If we think about it from a person perspective, not everyone uses the same devices, nor do they interact with them in the same ways. They don't necessarily have the same goals. And so even in this example here, I have 4 images from one of my studies showing 4 different hand poses for 4 different people interacting with the same interactive touchscreen-like surface. And so you can see that even dealing with just some different hand poses for the same kind of interaction, you can see that there are ways that this might impact or change a person's ability to perform certain required gestures or to hold devices while performing these different required motions. Furthermore, we sometimes fail to consider other assistive devices or other devices that people might be using, like wheelchairs, which can both create and alleviate challenges of interacting with computing devices. And so if you think of the wheelchair as from a challenge perspective, it can be obstructive to the user to be able to reach different surfaces or to reach different things in their environment or to reach devices. It also can be difficult to traverse certain terrain or fit through tight spaces. On the other hand, if we think about the wheelchair in kind of a more positive direction, it can also be used to carry and store multiple computing devices without burdening the user and with the ability to kind of hide the unsightly wires or to carry additional batteries. So there's these different opportunities that we might take advantage of. And so when I think of chairable computing, so what is a chairable? I use this definition to say devices that are designed to fit a wheelchair form factor, which maintain its shape and consider the abilities of the user in a holistic way. And so we'll use that definition going forward. Just to give kind of an overview of the research that we do in my lab, it spans a number of different areas, all kind of touching on accessibility in one way or another. But I work in clinical environments. I work in more thinking about maker spaces and participatory design. I work in the sports domain. I'll talk a bit about sports today, but also thinking about autonomous vehicles, navigation, and just the general relationship that accessibility has in interactive computing. I'm happy to talk about any of these topics. If I don't cover it in the talk, feel free to follow up and we can have many conversations about that. Uh, but for this talk, I'm going to talk about two main projects in kind of these three areas. The first, describing how I leverage the wheelchair in design for charitable computing. And then I'm going to talk about actually building suitable solutions or suitable devices for interaction on and around the wheelchair. And then talking about kind of the full arc of using Chairables to support wheelchair athletes with Spokessense and other wearable devices. So we'll dive into the first aspect of leveraging the wheelchair, which I like to describe as participatory ideation and design. And so if we think about the problem space here, we can start with thinking about motor impairments. And if you think about someone you may know, someone you may have seen or interacted with who might use a wheelchair, especially, we think of motor impairments, they can actually affect multiple parts of the body. In addition to the legs, they may impact the upper body, may present challenges to using the head, the neck, arms, and hands, especially for interacting or moving through space. The wheelchair itself, as I described, may also exacerbate some of those existing challenges given those motor impairments. So the driving question for this research was to understand, how can we design devices and interfaces that better support people with disabilities? So that kind of broad question. As the approach to this study, my approach generally involves understanding how people and technology interact together. What is the current state of what people are doing? What current practices, what current workarounds do people employ? And then understanding how we can build devices that meet the needs that kind of arise or meet those unmet needs in those contexts, which may involve building new devices or adapting existing ones. And so with this first study, our goal was to really understand wheelchair users' existing challenges with mobile devices and desirable solutions given their abilities. And so we began by conducting individual design sessions with power wheelchair users, and then continuing into focus groups to gain a broader perspective on potential solutions that went beyond the individual. And so we conducted those with clinicians to think about potential solutions that could work for a range of participants, a range of users. And then finally, we went back to individual wheelchair users to discuss their ideal configuration of proposed devices and solutions and techniques. And so to describe some of the findings from that work, I want to start with a story of one of the personas from our study. And so I'll start with this story of Kyle, who was a spinal cord injury, who had a spinal cord injury that he suffered as a teenager. And so he has paralysis below the neck. So he's able to move his head and his left shoulder. And so he has some residual motion that he can take advantage of to drive his wheelchair, per se, and to interact with some devices. And so he uses actually a head array or a set of mounted switches around the headrest or the headrest of his chair in order to control his wheelchair functions. And he also has access to some switches in order to use a smartphone, as you can see in the image on the right side of the slide. He actually uses a mouse stick with a stylus attached. And so he can actually point at the buttons as long as the device is mounted in a position where he can reach it and use that. And one of the really cool things about Kyle for the study was that he actually had his entire home renovated to be a state-of-the-art smart home. And so when we talked to Kyle about some of the challenges that he faced and about some of the potential solutions that he was interested in, it came out that when we think about this, especially in the context of this smart home renovation, he has controls that he can use this tablet, the single tablet, to control all the different devices in his home. He can open doors, change appliances, change environmental controls, set all of these different kinds of things. But one of the biggest challenges for it was actually that during the renovation, they had adjusted, all the doorways and counter heights and tables and things. But one of the dimensions that they didn't fully consider was the dimension of the tablet once it's attached to the chair. And so actually getting to the door, he could do that just fine once the tablet's attached. The actual tablet was mounted to a pole arm that actually set about 3 or 4 inches to the right side of the frame of his chair. So on the widest dimension, add about 3 or 4 inches to that. And that actually made it really challenging to get through a doorway with the tablet attached. So what would have to happen is that he would have to pull up to the door, remove the tablet, and then put it back on, or wait until he's out of his room in order to attach the tablet, and then he can go about the rest of his day. So there's this really inconvenient factor to having the tablet that then gives you access to all of these other things. And so he wanted to really change the positioning of the tablet, the ability to control those different devices, maybe through another type of switch, especially something that may be activated by his residual motion in his shoulder. So he could push a button with his elbow instead of having to get the tablet all the way set up. He could open the door and then attach the tablet in the room. And so he's really interested in those things. Or just a suitable display mounting, right? The simple solution is change how the tablet is attached to the chair, and then we've solved some of these problems. But this opened up a couple of other ideas, or this exemplified a couple of other concepts that we can carry over into designing for these scenarios or to avoid these scenarios in the future. One of them that's demonstrated is this idea of always available interfaces, which is common to wearable technologies. The whole idea of having the device on your body makes it always available to you. And so we want to carry that through when we're thinking about devices for wheelchair users as well. We also want to think about tailoring to the individual abilities of those users and leveraging whatever abilities that person has, rather than necessarily focusing on deficits or inabilities or impairments that that person may have. We want to tailor it to the way that they do want to interact or the way they can interact. And then finally, maintaining the silhouette and shape of the wheelchair and the user together, which turns out to be one of the core values for charitable computing. And I'll come back to those in a little bit. And so from the individual interviews, we saw a range of solutions. We interviewed several wheelchair users, so everyone is a bit different. Not everyone has the same exact needs. So we wanted to gain kind of a broader perspective outside of those individual solutions. We went to clinicians at a local rehab hospital, a spinal cord injury rehabilitation clinic. We conducted 4 focus groups across 4 days, where we used personas based on the prior participants, as well as people who were actually there in the clinic to think through designs. And so on each day, we actually had a different type of interface that we focused on, or a different topic progressively. And so we had about 17 clinicians participate in these focus groups over the course of the 4 days, and some did repeat day to day. So on the first day, we had them design a phone dialer, an accessible phone dialer that can maybe be attached or implemented around the chair. The second day, we had them design a game controller. On the third day, we had more of a broad focus on input techniques. So after having designed specific devices, we asked them to think about just how does a person input the information to a system? How can they interact or perform an action and have the system do something? And on day 4, we had them focus explicitly on how the user would get feedback, either from a specific device or in general. So thinking about outputs and displays. We took the results from those focus groups back into individual design sessions. So from those 4 focus groups, we ended up with a set of inputs and outputs that were desirable input and output possibilities, including wearable devices, removable displays, integrated buttons, head-mounted displays, projected interfaces, and things like that. We took kind of the full set of those into these individual design sessions, and actually with 7 power wheelchair users, and asked them to generate their ideal setup. So if you're thinking about what inputs and outputs would work for you, let's describe that using a model chair. And so we first had them, on a diagram similar to this one, we had them actually just identify reachable areas on the chair that they could interact with something, or that they could see an output, whether it's providing the input or seeing an output. So all the potential possibilities. Then we had them actually describe which inputs they would want, and then where they would want to put those inputs, where they want to put those outputs, describe what the functionality would be for that input or for that output. And then we asked them to rank their preferences among all the different options that were presented, the general input and output types. And so as a result of that, we came out with a list of interactive input and output preferences. On the input side, we had wheelchair integrated and wearable inputs as kind of the preferred types of inputs, removable interfaces third, and gesture-based interactions as kind of the 4th ranked option. And when I say gesture-based interactions, in this case, I'm speaking about kind of in-air motion gestures with your hands or arms, not gestures that are performed on a screen. And so on the output side, head-mounted displays were kind of the most popular at the time. If you look at the timestamp, this was about 2013, 2014. Google Glass had just been released. And so this was a very new, fascinating idea to be able to have a private display right at your eye, right at your head, something that you could use, and it would be completely to your individual self. And so that was really what kind of drove the preference there. I say that because the next option was add-on screen. So just having an additional screen, the same as you'd have a tablet or phone mounted, or the second screen that some folks already have attached to their chairs. And the third option was projected interfaces, which was another kind of futuristic concept of if you could have a projector attached, a mini projector attached to your chair, and pull up to any surface and turn that into an output area, whether it's a wall or a desk or a table. That was the third option. People were really interested in this idea, but were really turned off by the idea that if they get a text message in the middle of a dark theater, they'd have to pull up to the wall in the theater and put their own movie up and their text messages there for everyone to read. Right? So privacy was a major concern, and so it kind of drove the ranking preferences down for that. And so coming out of that, thinking kind of holistically about the whole study, one of the major takeaways from that initial exploration, that initial multi-method study, was this thing that I call the Chairable starting five, or the design principles that we carry forward into Chairables. And so the first one is availability. So thinking, again, capturing that devices should be always on or always available. And the second one is maintaining the silhouette of both the user and the wheelchair together. So we shouldn't be designing devices in the first place that just attach. We should be thinking about how they actually fit with the body in the same way that we think about how wearable devices attach and change the silhouette of a user. The tailoring, so again, accessibility tenet, so thinking about devices that should be tailored to individual abilities. Familiarity to known devices and systems should be considered. And so this can have both positive and negative implications when you're thinking about adding a new device. People will carry over both the positives that they think, the things they think will be positive about interaction, but they also carry over some of the negative sides or negative perceptions. We'll get into that also a little bit later. And then finally, robustness to different environments and conditions of use. And so I can't stress enough that if you think about someone using a wheelchair, you realize if you think about someone who goes through their day, you probably don't spend your entire day sitting in the same room or even sitting in the same chair. And so you move through spaces, you move inside, you move outside, you go to work, you come home. And the same thing is true for people who are using wheelchairs. It's something that is an immutable fact, right? People are going to use them in different conditions. So whether it's rain or shine, dust, snow, hail, we should be designing and thinking about how these devices are going to interact in different environments. And so as an instantiation, or as kind of a first implementation of a Chairable for integrated control, we built the Jest Rest. And so as we're thinking about what a Chairable actually looks like, so after I describe this kind of abstractly, always on, always available, wheelchair integrated inputs and outputs, this image comes to mind. If you're a Star Trek fan, you probably recognize the chair, the captain's chair from the Starship Voyager. In this case, the captain's chair, no less. You understand the captain's chair is where the captain sits, and the captain is in control of the ship. If you really think about it, if you think back to all those Star Trek episodes, whoever actually sits in the captain's chair is actually the one who's in control of the ship. It's not actually the captain. It's whoever's in the chair at the time. And so we carry that idea of the chair as a command center into this concept of Chairables. The captain's chair on Star Trek also happens to have the inputs and outputs in the exact same place that our participants wanted them to be, which is right at their fingertips, where they have either the highest dexterity or the highest concentration of control at the ends of the armrests of the chair. So we knew we needed to build an armrest-based interface at the edge of the armrest on the chair. So we set out to do just that. And so I'll go back to this image from before. When we think about who is actually going to be using that device, so hopefully I've given a little bit of variety, but I'll go into a little bit more about these different hand poses. The people that we're interacting with these computing devices have a lot of variation in the way that they move and the hand positions that they may be using to interact with a surface like a touch screen or another interactive surface. And so in this image, you can see on the top left, the person with kind of an open palm interacting with that index finger. For reference, all of these participants are performing the same swipe gesture in the forward direction on this touch surface. The person on the top right has a more loosely clenched fist, and they're kind of resting those two fingers, the pinky and their ring finger knuckle, on that surface. The person on the bottom right has a more tightly clenched fist and is interacting with more kind of the bottom of that fist on their palm side. And then the person on the bottom left actually has a much more severe contracture of the arm. And so they actually have to kind of crane over the top of the surface and interact with the top of their finger pressing downward in order to get the proper leverage to perform the motion. And so it was important for us to choose both gestures and interaction type or sensing profile that would be robust to all of these different types of hand poses. So we didn't want to go with a normal capacitive touchscreen. So we used actually a force sensitive, pressure sensitive touchscreen or pressure sensitive surface instead of a touchscreen for this. And so the Gest Rest is an armrest based gesture input device using force sensitive resistors instead of capacitive touch to capture familiar touchscreen gestures as well as some special gestures designed just for the armrest. And so as you can see in the image, have now already seen the image on the left where we have the surface kind of covered up. When we peel back the tape and give you kind of a more under the hood view, we have an array of sensors arranged in a grid so that we can tell the X and Y positions of force being applied to the surface. We used the Arduino microcontroller to enable this and processing to build a simple interface that would allow us to just use a simple recognizer to capture the individual gestures people performed. And so, like I mentioned, we use this for traditional touchscreen gestures. So you can think taps, swipes, drags, flicks, and things like that. And we use just the center of force that people apply to the surface in order to detect those gestures. But we also thought about how, because we're using a different form factor, it's in a specific place, we thought about special gestures that are specifically for the armrest. And so if you're sitting in a chair that has armrests on it, feel free to try some of these out. I'm pretty sure you've already done several of them as you've adjusted your position. But think about the intentionality of it this time. And so these 5 special gestures we use for the armrest that you may not perform on a traditional touchscreen. The first one being the squeeze gesture. So as a deliberate input, you might squeeze the edge of the armrest, and that may indicate something to the system, right? Something we can capture as a deliberate motion. The second one is the lift gesture. So it's an arm rest, not an arm raised. Most of the time, your arm is resting on that surface. And so deliberately lifting your arms off of it or lifting a hand off of that surface can be treated as intentional input. The punch gesture, which was my favorite, is the one where you apply a sharp downward force onto the surface, which we can then detect using the force sensitive surface. On a capacitive screen, you might be able to detect it, but you've also probably broken your device. And so the roll gesture and the rock gesture are kind of in one direction. You roll from one side of the surface to the other is the roll. And if you're rocking, you roll from one side and then back again. So we wanted to actually capture these. Following a similar approach to the previous study, we involved both individuals and clinicians to gain that kind of individual perspective and broader perspective on potential use of these surfaces by multiple people. And so we are specifically interested in how well our force sensitive version of the interactive surface would work. But in order to understand whether the location of the device or location of the input was also a major contributing factor, we also wanted to replicate some other common input types and move them to the same position to see if that would change people's preferences with regard to the device. So we created a single button version, a 4-button version, which arranges the buttons in a directional pad. And we also created a touchscreen version, which simply adds a capacitive touchscreen to the end of the armrest. And we actually compared all 4 of these in a study where we asked participants to perform each of these gestures, interact with a simple interface, and then rate and rank their preferences for both devices and positioning of the armrest, right? And so doing that, we asked them to rank their preferences. And so thankfully for us, it was a very positive result that the force sensitive version of the Gest Rest was actually still preferred by both wheelchair users and clinicians. However, we did find that just having those inputs in the right location at the edge of the armrest and having them be available to users, it was easy for people to use. People did find it very convenient. But the thing that set the force sensitive version of this apart was actually the flexibility that was offered by the force sensing interactive surface. So again, this is one of the positive times that the carryover familiarity to the touchscreen, the similarity was a major benefit here. They could use all of the same touchscreen gestures, but now they could use those touchscreen gestures on a surface that would recognize their different hand poses or even different tools that they might be using. One of the things that was really special that came out of the clinician side of this was when thinking about how these devices would be interacted with by their patients, one of the things they mentioned was on the armrests of the chairs, what they often have to do is to provide proper support for individuals' hands. They often have to build up using foam or clay or some other medium to actually support the hand in the right position. And so they were concerned with a lot of the solutions because if they needed to adjust it, it would cover up the interaction surface. And so for a capacitive surface, that means the entire touchscreen is now unusable because they covered it with a block of foam. But for the force sensitive version of this, you can interact with it the same way. The force transfers through this dense foam that they've placed. So you can see in the middle image, they placed this block of foam in between. They can still interact and perform all the same kinds of gestures through the foam. And so that was really what set it apart. And so that was kind of our first example of a chairable device attached to the chair, kind of implementing all of those different aspects of chairable, the starting 5, with the exception maybe of robustness, because this device was not put through all the rigorous testing that it needed to be. And so that's ongoing work for us, is to really refine the interaction and to build out its environmental viability. And so for a brief moment, I'll talk about what's next for that kind of line of work, thinking about interaction and intelligent wheelchairs. We're still examining new interaction techniques for wheelchairs and thinking about how we can apply emerging interaction techniques, new types of gestures, new types of sensing to leverage the broadness of ability for different wheelchair users. What kinds of things might be leveraged differently? What kinds of combinations and features of different sensing or multimodal interactions we can build here? But also thinking about how autonomy plays a role. We recently finished up a study actually asking the question of what does it mean to have a smart wheelchair? Oftentimes we think about robotic wheelchairs, we think about autonomous driving chairs, but for the people who are actually using these chairs every day, what does smart actually mean? Is it intelligent in the AI sort of way, or is it intelligent in a design sort of way? And we see kind of a mixed result from that. And so I'm excited about what's coming out of that study. I'm happy to talk more about it in the Q&A if you're interested. I'm going to take a pause here before we shift into the next project, which is Chairables for athletes. And I see there's some questions in the chat. I can come back to those as well. So for the remainder of the time of the talk, I'm going to talk about a project called Spokessense, which draws on both ideas from wearables and thinking about chairables for athletes specifically. Think less about think the specifics of a power wheelchair and more for people who are performing very active physical activity and how we can see that. And so again, the driving question in this case that kind of sparked this work was thinking about how to design inclusive or more inclusive activity monitors for people with differing abilities. And so you'll notice that there isn't a wheelchair in sight in that equation, in that question. We didn't set out to do this work and to design something specifically for a chair. We were actually just thinking broadly about physical activity, people with disabilities, and the broadness of wearable technology. So again, the problem here, we're thinking about, activity monitors and fitness trackers are gaining popularity. At the time we started this study, Nike, Fitbit, Apple, Under Armour had all just invested multiple hundreds of millions of dollars into their products, into their programs to develop these products out. But we were still seeing this kind of low adoption of these technologies among people with disabilities who were purported to be really have a really high potential to benefit from these technologies, especially given concerns of inactivity or concerns of sedentary lifestyles, given less access to the environment. And so we conducted a number of different things to really to get at this question. We started with just an analysis of what consumer wearables were out there. So we found a database that had both currently available products as well as kind of Kickstarter products that were coming out in the future. We had conversations with experts about the design of wearables at different companies, as well as research labs. We conducted semi-structured interviews with wheelchair athletes and coaches. I'll talk about observations that we did at the National Wheelchair Basketball Tournament when I get into the specifics of Spokessense, and then actual development and testing of a device. And so if I wanted to summarize the results of our consumer wearables database, you would see something that looked very similar to the Apple Watch on the screen here. And so notice there's a bit of variety in the actual watch itself, but generally speaking, a lot of the devices were primarily wrist-worn devices that had some kind of a display or an LED. Many of them had some kind of a watch or a clock face, some basic motion sensing, and a button, right? A way to provide some kind of simple input. So most of the devices we saw looked like this. As we started to dig into the challenges and the approaches that people were adopting to get to create different wearables, you might ask, if you're thinking about physical activity, one of the biggest, some of the challenges that we saw after conducting these studies, there are a lot of challenges that came out of it. But as far as accessibility, as far as adoption was concerned, we saw some of these kind of dichotomous relationships between different aspects of the wearable. And so if we think about the first one is body location versus sensing. And so some of you may remember foot pods, the Nike foot pod. I think Garmin had one as well. There may be a couple that are still around. But it's this device that attaches to the shoe or attached to the shoelaces or is actually embedded in the shoe and gives you feedback on your things like heel strike, your cadence while you're walking, number of steps, and things like that. And so that device, that sensing, is inherently tied to the shoe that you're wearing. And so if I put to you the question of what if you don't have a shoe? What if you don't have a foot that you attach the pod to? Now that device is completely useless, no matter how innovative it is, right? And so you may be thinking, well, that's a motion device. It attaches to that specific body location. We can use other types of sensing. We can also sense other types of things. So instead of doing motion, for exertion, maybe we can do something like sweat sensing. And this was another innovative exertion technique for understanding how active someone was. We can detect certain enzymes in the sweat, and they are linked to the level of exertion that a person may experience during an exercise. And so again, in the image on the bottom right, you can see this wrist-worn sweat sensing device. In addition to the case of what if you don't have a wrist or to attach the device to, maybe you could put it in a different location. One of the things that I learned in my time at the spinal cord injury clinic was about a condition called hypohidrosis, or the inability to sweat below your injury level for someone with a spinal cord injury. And so in that case, someone who has a very high level injury may say at the neckline, this wrist-worn device at that point is not getting a full signal because the sweat is not being produced in the same way that you would expect at that point on the body. So we have to start to think about how those different devices interact. All of that coming together, all of that being said, the biggest challenges that we saw from our studies was actually misperception of what the devices were capable of or what the devices were doing and for whom. And so the first quote that kind of came up over and over and over again, especially for wheelchair athletes, was that these devices track steps and I don't take steps. I'm supposed to take 10,000 steps a day while I'm in this chair and I'm pushing around. I'm not taking any steps. It's not going to do anything for me. This is another quote from an avid hand cyclist, mother of 3, who is also an elementary school teacher. I'm sitting, yes, but I'm constantly rolling around. I'm always interested to know not steps, but how much I'm actually moving around because I'm never immobile. So just to clarify, this image is not of the participant. This is an image of Tatiana McFadden, who is a Paralympic racer. But what these kinds of quotes, what this quote, the other one, these kinds of things revealed to us was that not only are the words and the perceptions of the devices different, but in some cases, the actual activities and information of interest is also different, which led us to ask, what would appropriate solutions in this space do? What would they look like? And how would they actually be used? And so inherently, I chose to do this through sports. And so why did I do that? In general, if we're thinking about sports, we think about a metrics-driven activity, whether it's digital or not, competitive engagement in physical activity. So you're well motivated to actually perform the physical activity rather than having to find people who are physically active regularly in their everyday lives. But also, if you think about sports at this point in time, none of them are without data. Most of them are really just about the numbers. We think about talent now, but everything is just numbers. Baseball, I think, is really just specifics, and it's just statistics at this point. You have some numbers, but you have some people running around the bases and hitting the ball, but it's really a conversation about numbers. So I chose basketball, and I decided to start with wheelchair basketball as a first project, partially because of my personal connection to basketball. I've been playing basketball for most of my life. And so when I started this project, I got involved with the National Wheelchair Basketball Tournament, where we actually were able to get involved and get in touch with athletes. And so to give you some background on wheelchair basketball before I get into that, it is an adaptation of traditional stand-up basketball that's been adapted for use using a wheelchair, as opposed to a sport that's been completely developed for the population or for a particular group of people. It has evolved to, at this point, using specialized athletic wheelchairs with wheels at particular angles. They're made of lightweight materials for maneuverability, and they have different centers of gravity for each individual athlete. One of the other innovations of wheelchair basketball and several adaptive sports is also the addition of the functional classification system, which allows for kind of equitable competition when thinking about people with disabilities, people who are using wheelchairs. Not all of them have the same abilities, not all of them are impacted in the same ways. And so how can we both level the playing field and give everyone an opportunity to compete at the highest level? And so this classification system essentially assigns a point value from 1.0 to 4.5 for every athlete based on their ability to perform specific motions related to the sport. So someone at the 4.5 end of that scale has very little to no difficulty performing all of the required motions for playing basketball, has perfect trunk control, the ability to turn, reach, stretch, and shoot. Whereas someone on the 1.0 end of that scale may have more difficulty moving or performing those different actions. And so as a team, you have 5 players. The total number of points for your team can't exceed 15, which means you can't have all players at the 4.5 level. And so there's actually incentive to mix the team up and also mix the team up of people with different abilities. Right. And so I'm going to go into Spokessense as the solution that we and ultimately came up with. So I'll give you the solution first and then talk about how we got there. And so this is Liam, our unofficial spokesperson for Spokessense. He volunteered at the tournament to take this wonderful photo of holding the device in his hand. So there's a small sensor on that device that's designed to track the activities of wheelchair athletes. And so how we got here, we started with doing some early studies starting at the National Wheelchair Basketball Tournament, which, if you're unfamiliar, is an annual event which brings together about 1,000 athletes over the course of a weekend to compete for 6 championship trophies across 3 adult divisions and 3 youth divisions. And so for a sense of scale, that's about the number of games that are played in this tournament is almost equivalent to March Madness crammed into a weekend. So March Madness, the basketball tournament for all NCAA, into one weekend. So 88 games on the first day until you have those 6 champions on Sunday. At this tournament, we conducted interviews and a 76-person survey of athletes and coaches to talk about the metrics and things that they were interested in, metrics, form factors, and all of the things that surround that. And so coming out of that, our formative results at the beginning of that, on the metric side, people were really interested in motion, movement, speed, acceleration, and distance. And they were also interested in the number of pushes, which at the time had just become available using wheelchair mode on the Apple Watch. So people were actually able to use that in practice and move forward through that. They're also interested in kind of fatigue and stamina-based metrics and physiology, things like respiration and breathing, as well as heart rate. And this is a ranked list of their preferences. So they're really interested in movement, speed, acceleration, and distance. And one of the reasons for that is if you think about how we move, how you take steps, your steps aren't always the same length. And so knowing the number of pushes is helpful, but doesn't give you the full story. You can push softly and go a short distance. You can push hard and go a long distance. You can push once and go an entire length of a basketball court and back. You may have to push 15 times to do that. So it doesn't give you a complete picture. They're much more interested in the details of those movements. On the on the form factor side, we found that the form factor of the devices was extremely important. So we went in thinking, okay, we want to think of what kind of wearable device would be helpful in this scenario. We found that people were really interested in something that could attach to the chair. Not necessarily to get at these specific metrics, but actually to get around a limitation of the rules where you have a wrist-worn device. If you're wearing a wrist-worn device, it might be considered actually jewelry and not permissible during competition when you really want access to that data. And so we're starting to see these rules slowly change, and some of these things are now allowed, but at the time, you were not allowed to wear anything like a Fitbit or an Apple Watch in competition because it was jewelry, and you wouldn't be able to actually get access to this data. So having something attached to the chair was extremely appealing, which was great for me thinking about Chairables and giving us another opportunity to develop something. We were not the first to think about attaching devices to the chair. And so there are existing wheelchair-based trackers for other wheelchair sports, and for basketball as well. Devices like data loggers that you could attach to the spokes of the chair, or even something that you might wear. So this is what's shown in the figure at the bottom is actually both a wheelchair attached sensor, a data logger, and a device that you could actually wear to give you kind of GPS positioning of a player on a court. But at the time, access to the data from these loggers was often delayed. So we think about, days or even months, weeks or even months before you're actually able to analyze and provide feedback based on that data. In the moment is when you really need to change that. And so having access to real-time data was something that we were really trying to deliver on. So we created Spokessense, which was a prototype device for wheelchair basketball to provide that immediate feedback on motion-based metrics for wheelchair basketball players. And then specifically, we were interested in providing information about speed, distance, acceleration, tilt, and other things about moving around in the chair. And so I'm going to briefly talk about the interface and the study that we conducted in 2018 at the wheelchair basketball tournament. So first, the prototype. So we combined a photon microcontroller, a 90-degree of freedom, IMU to capture motion and orientation. We included a microphone for getting some environmental and contextual factors, and I'll describe a little bit about that as well. And we created a custom housing to enable us to attach this device to the chair in a specific location over top of the quick release axles on these wheels. For the interface side, we wanted to keep it very simple, especially for our testing. The first implementation of this actually processes all the data offline on the host device and on a smartphone or on a laptop, and provides just the numbers, mostly just the numbers on those metrics, as well as a kind of estimation of exertion levels in these different speed zones that are shown at the top. And so we're detecting both acceleration and braking, which turns out to be extremely important in wheelchair basketball. How fast you stop is almost as important or more important than how fast you get going. And so we provided all of that in that interface. I mentioned orientation changing and things like tipping and tilting. So not only do we detect obvious orientation changes, like when someone has maybe tipped over completely, which you can imagine there is, definitely for safety reasons that might be important, or for understanding potential injuries that might be of value. But we can also tell when they've tilted and stopped or balanced up on those wheels. And so in wheelchair basketball, one thing that athletes will do in order to gain a height advantage over your opponent, say for a jump ball or a rebound, is actually tilt up onto those two wheels and reach up over top of your opponent. And so I'm going to show this video to demonstrate the level of skill that someone can get to using Pat Anderson. So you'll see he's tilted up on there. He actually takes the wheel off using that quick release axle while still balancing, throws the wheel away, lets it roll around for a while, then catches it, reorients it, puts it back on the chair before coming down.
Well done.
And so that's about a 30-second tilt, right? You're tilting and balancing and staying up there. It's a skill that you'd want to develop and a pretty challenging thing to get started with. And so we want to be able to give athletes feedback on the things that they want to practice, so we can tell whether you've tilted or whether you've tipped all the way over. As I mentioned, we also included a microphone on the device, and we use this to capture environmental features that also may indicate events of interest in a data stream. So if you imagine we have all of these metrics, all of these numbers occurring over a period of time. Let's say you're playing a game. A basketball game typically lasts anywhere from 30 minutes to 2 hours, depending on who you're playing and how you're scoring and who decides when it ends. You imagine one session of that data, where do you even look? Where do you start to see if there's something interesting that you want to analyze or give feedback on? And so what we did was we wanted to use, in order to facilitate review of the data, we implemented a very simple game sounds classifier based on a project called Ubacoustics, which allows us to capture or use a small sample of recorded game sounds and combine that with audio collected through existing sound libraries in order to train a model. And we were able to achieve about 98% accuracy for these 3 game sounds of the buzzer, dribble, and whistle. And so during these different games, we can then, by detecting when a buzzer happens, which is usually the end of a quarter or at a substitution, we can tell when someone's dribbling the ball. So while you can do things like detecting your speed and motion while dribbling or without dribbling, whether you're close to the action on the court or whether you're farther away from it, as well as when the whistle blows. Anytime the referee blows a whistle, something important just happened. And so we can then drop markers automatically into the data stream for people to then pick up on a review later. And we tested that actually during the Division I tournament championship game. So at the tournament, I think we got a little bit of time left. At the tournament, we actually tested Spokessense during these live demonstrations and interview study. We allocated about 25 minutes for these. We wanted to keep the interactions pretty short. People were not there to participate in research studies. They were there to win championships and win trophies. So we had kind of a free demonstration and a 10-minute interview to get some feedback on this, but allow people to explore actually using the device on their wheelchair. So they could either use our wheelchair and jump into it if it fit them, or actually attach our devices to their chair. We had about 50 people try out the device during the tournament that year. And I'll talk a little bit about some of the feedback on kind of the utility of that device, the utility of the data that people saw coming out of it. And so the first main thing was the idea of goal setting and having that immediate feedback. So having that immediate feedback for in the moment during training or practice sessions, as well as being able to adjust things during a game, but also being able to set goals based on their known performance data rather than having to just kind of set an arbitrary metric. So the example that I like to use is if you're at this point, sports like biking will tell you this is how fast Lance Armstrong was at this part of the Tour de France. If you want to be like Lance Armstrong, this is where you need to be or where you need to improve. When you have the metrics, you can do that. The most interesting thing that I think came out of the study was this idea of access to casual comparisons between peers or elite athletes. And so to kind of ground this, this quote from one of our participants was, if Steve Serio's top speed is 10 miles per hour, I want to go 11. And Steve Serio was a 2017 SB Athlete of the Year, a very well-known wheelchair basketball player. But this is one of those things where if you have access to that data, you can make that comparison. We also saw people really interested in being able to evaluate their intuition. So being able to compare between different players with similar abilities or similar classifications in that functional classification system, different regions. How do I compare to other guards or other 1.0 players? Being able to ask those kinds of questions, or being able to support your intuition with data. So if you're competing with the same team a lot, you kind of know what to expect based on intuition, but this would add that objectivity that people are looking for to confirm those intuitions and actually make adjustments according to it. One of the most fun parts of this study was this idea of facilitating competition through data. And so what appears to be a humble stretch of concrete on the left side of the screen became an intense battleground once there was data involved. So just by putting down the cones, people passing by would start to just roll through the lanes, to kind of move over in their path. You can see someone next to it. People would just start to roll through the lanes and think of it as an obstacle course, or maybe weave through the cones. But once we put the data up on our large screen and showed someone go through and see their top speed, it became something to be the best in the building. And this gentleman here came back to our booth at least 6 times to make sure that he was still the fastest player at the tournament that year. And I remember there's 1,000 athletes there. And so he really wanted to make sure. He came back morning, he came back evening, he came back in different chairs to test just how he could do that. And we did have a pretty good battle going on between him and one other person. And I think the top speed, he ended up leaving as number 2 with a top speed of 12.5 miles per hour. The top speed was 12.7 miles per hour. So pretty fast. And also something that you can now do without, getting both of these athletes together and having them actually race. And then finally, for utility's sake, the ability to augment existing review practices. So being able to assess things like endurance and consistency across different sessions or across different games, across different practices at different times of year. But then also being able to have immediate feedback on that to say, hey, in March, this is how fast you were going. Right now in this practice, I know you can do better. You're slow on this turn. That last turn, you could shave off this amount of time. I know you can do it because the data is over here. But then you also have these additional layers for post hoc review once you actually give this immediate feedback and are able to kind of pull that out. As far as where this work is going, there's ongoing development on this project, refining both the sensing techniques, refining the sensors, refining the form factor. And we're aiming to use this both in wheelchair basketball, in other sports, and in other sports, in addition to athlete performance, looking at how we can use it to support team management. So being able to feed the data into maybe predictive algorithms or things to help with lineup management, to manage that kind of balance between the functional classifications, the point systems, and as well as your competitive strategy. We're also looking at other sports, other wheelchair sports. As we understand this domain, we're also interested in how this will translate or how this can also be applied for everyday activities that aren't sport specific. And then since we have the sensors there, we can also leverage this for input or explicit input for another system. Right? We've just finished conducting another study looking at technology roles in adaptive sports, just thinking about the broad role of technology for facilitating competition among adaptive sport athletes and also for health and wellness and fitness applications. And so we're excited about different opportunities for technology to enable a number of opportunities in these different sports. So beat baseball or blind baseball, wheelchair tennis, rugby, and even hockey. And so with that, I want to thank all the collaborators and funders that have made this work possible over the years and who continue to make this work interesting, exciting, and impactful. And I'll thank you all for listening and open for questions.
That was fantastic. Yeah, so if people have questions, feel free to put it in the chat, or you can also raise your digital hand. Go ahead. We've got one from Monica. So Patrick, how did you recruit the individuals for your new study?
So in general, recruiting, it would help which new study? A lot of new studies. A lot of the sports work, we actually reached out to, we reach out to local sports teams, we reach out to national sports teams. I've worked with national organizations to get in touch with coaches and administrators. So we've kind of run the gamut of ways to reach out to people, from cold emails and cold calls to posting in Facebook groups or just showing up at practices when that was still possible. Monica.
Oh, can you hear me? This is Monica.
Yes.
Just wondering, that was for the first study with the gestures, because my worry is that the people that we recruit sometimes are more closer to the city centers or to some of the organizations that are in the city. Mm-hmm. Maybe some of the accessibility components are different in people that live elsewhere. And I was wondering how we can kind of create a broader reach to everyone else in our research.
Yeah, so yeah, that's a great question. And one of the things that I think the last year has definitely taught us even more lessons in. Kind of the first set of approaches that I was fortunate enough that the spinal cord injury clinic that I was working through, so I was actually recruiting participants at the spinal cord injury clinic, kind of in the lobby, or with the help of different clinicians. They would suggest people, and then through word of mouth from those participants' friends and families. But this clinic in particular draws people from all over the country and all over the world. And so people would come to the clinic from different environments, not necessarily from living in the city or around that clinic. And so when they would participate in our study, and they would go back home and they would tell other people that this is an opportunity. For the physical study, this was really difficult. So actually testing the physical devices was definitely something you had to actually be in the city for. But then being willing to travel is the kind of other component of that. In the virtual space of over the last year, when we've been conducting some of the smart wheelchair studies and thinking about sensing and doing the interviews, a lot of that has been through virtual sessions and thinking about what kinds of workarounds we can have for showing off different parts of the chair, taking pictures, exchanging that, adjusting cameras, and really overcoming some of that. But a lot of it is just traveling to new places, traveling to those other environments.
Just one more follow-up question. Did you sense any differences between the people that were living in city centers over the people that travel to the location?
So there's definitely a couple of different things that I saw. I think the most salient ones were the types of devices that people might be using. In city center, you see a lot more, smartphones. You see a lot more more of the latest technologies versus people living further out, like whether it's suburbs or rural environments. You see a lot more people who've adjusted devices or have older devices that are just as smart, just as capable, but they have been modified. I saw a lot more DIY devices and a lot more do-it-yourself AT solutions from folks beyond the city. Right? And so when I conducted that study, it was in Baltimore, Maryland.
Oh, that's interesting. Oh, thanks so much.
Hi, so this is a great presentation. My question was, Jim, so when you do this participatory design studies with folks who use wheelchair, do you also include their immediate family members or caregivers in the study? And if so, what your experience has been like?
So yes, that's another great question, and I didn't touch on it very much in our. There was another benefit for why we separated out individual design sessions and clinician design sessions, was to start to get at that caregiver versus individual user perspective. And when we do have kind of close family members, we do try to involve them in studies as much as possible, both individually and together, because you get different answers, right? Oftentimes, especially with assistive technologies, the caregiver is using or impacted by the assistive tech as much as the person it's intended for, or even they're the primary user of that tech, and the person who's actually using it is interacting with it in a different way. And so we're always trying to balance this idea of interdependence that relationship represents, where it's not necessarily that this person needs complete independence, they should always do it by themselves, recognizing that they're going to still have support, or recognizing that they would like to still work with other people. We also have to consider that, especially in interface design. There's the dark side of that question is sometimes the caregiver has a completely counter position on that, where the caregiver actually wants the person to remain dependent and the person wants to be independent. So that's also another thing that we try to tease out in our interactions.
Thank you.
People are great.
So I guess Rachel had a question in the chat. So she says, I've heard that the pandemic has actually been beneficial to people with disabilities, as it gave them more freedom to work from home and not have to navigate the challenges of commuting and getting around an office. Are there any other pandemic fueled innovations you know of that have benefited people with disabilities?
So I would say that's also another great question. I'd say that those have been kind of the primary benefits that I've seen. I think from a research perspective, or from the technology design perspective, we've been able to reach more people as the tools have improved. So I would say the advent or the necessity of virtual conferencing for the general public has made it so that virtual conferencing has evolved significantly faster than it would have otherwise, which means that we can do a lot more, which means that the accessibility of these tools is thought about much sooner than it would be otherwise. And so I think, again, it really seems like, getting around the challenges of commuting, getting around the challenges of interacting, but also just having a focus on how difficult it is to actually interact with and use these interfaces, since we have such a large number of people using these devices for the first time, or using these systems for the first time. For us, it's really been great to see how active people are and how connected people are on the internet connected spaces. Social media, I think, has kind of blown up in terms of being able to connect with a broader audience and having people be willing to connect through digital means. We're also looking there more as researchers. I'd say other researchers are now looking there more. We've been looking there for a while.
So I just have a general question on these charitable technologies like Spokessense. Are these like DIY kits that individuals who use wheelchairs can assemble themselves, or especially for sports teams, someone else does it for them?
So there's a bit of both. Our goal is often to build kind of a reference device. So especially being the academic research lab that we are, it's how do we abstract these components such that they can be built, such as they can be built, such as they can be replicated. At the same time, some of the, at least especially some of the components for like elite athletes are, longer collaborations that we would have to work with. The solutions are, one-on-one. Our goal is such that the athletes and the participants themselves can assemble these devices, modify them, and use them in the way that they would like to. Adaptability is key, especially for access technologies. And so we try to do that, but while maintaining a low cost factor. The cost of these devices is also another major factor in whether or not someone's going to use it ultimately. The wheelchairs themselves are a few $1,000s. And so if we're asking you to then add another $1,000, multi-$1,000 tracking device to it, it's not a very compelling proposition. But things like I'll say the Just Rest, our immediate goal with the Just Rest was to produce a kit that people would be able to assemble themselves and attach to their chair, remove it when they don't want it. Spokessense is more of we'll produce the sensor package that works really well and then replicate it.
Thank you.
Yep.
I have one question. Sorry, I was typing. For Patrick. So, given the variability in the different abilities and the physical, like the bodies, how do we create that pattern, the pattern library that we can use to reuse in something like Chairable?
But that's one of the values or one of the benefits of Chairables, as I see it, is if you think about all of the people who are, one of the reasons why Chairables is so compelling for me is because if you think about all the different people who use wheelchairs, it captures actually a large swath, a large variety of people. And the commonality that they share is that they're using a wheelchair. They're using a manual wheelchair, they're using a power wheelchair. The chair itself can be customized in many different ways, but there's still a relatively finite set of things that you'll find for how someone might adjust the chair, right? And so if you use that chair as kind of the jumping off point, the same way we think of how do people use a smartphone, it's a rectangular device in your pocket. How many different ways can we augment that so that a larger number of people can use it? How many different ways can we augment a chair? The way that someone sits in a chair, where you can place things. I think there's a lot of opportunities there, but also not being wedded to specific positioning of devices, but also understanding that there's freedom now with the chairs, that the constraints of wiring and the thinness of a display or how small something actually needs to be such it's out of place, you can actually move that and you can make progress in that space and solve the full problem later, right? We can build a really ugly set of wires and sensors, place them in the right places, and then refine and still have something that's useful and impactful today, right?
Oh, thank you.
Looks like Ryan has a question.
Hi, yeah. You mentioned that gesture tracking seemed to be a bit less popular from the others. Is that partially because of the tactile nature of it? Like it's not, it's sort of moving in the air instead of touching those surfaces or interacting with them and getting haptic response of some sort?
So all of those things, and so definitely all of those things. There's the haptic nature of it, being able to touch the surface. You have some confirmation, you have some feedback to it. There's immediate feedback from performing the gesture, as long as you have the sensation to capture that. Also, touchscreen gestures also tend to be very fine-grained and not very tolerant of differences. And so for a lot of folks, they were very concerned that they'd be able to perform that exact straight line or that exact squiggly line that they needed to produce. Anecdotally, or one of the other things about open in the air gestures is as I wave my hands around to perform the gestures that I'm doing, you all will start looking at me. So I draw a lot of unnecessary attention. I'm already sitting in a 300-pound wheelchair. I don't need to be doing all of these other motions as well.
I wanted to just add another thing. There are some sort of muscle tracking devices as well. Have you ever used something like that? Like not getting into like EEG or brain tracking, that's probably still too early to really be super useful in most cases, but muscle tracking seems to be very precise and quite subtle comparatively.
Yeah, so we haven't used it yet, but it is definitely one of the promising approaches for kind of this additional, what other devices can we build up in this multimodal platform space? Doing muscle tracking, especially when we're thinking about residual muscles or amputees, the muscles that you would be tracking for hand and finger motions are still oftentimes intact. And so we can actually leverage that as well. So great point.
Cool.
Looks like Shuo has a hand raised.
Thank you. Thank you, Patrick, for the presentation. So I have a question about the design principles you mentioned earlier in your presentation. So the availability and adaptability and so on and so forth. Can you elaborate more about how did you reach those design principles, and is there any other type of assistive technologies that can apply those principles?
Absolutely. So let's see, I'll actually just go all the way back to the slide. I can say the way that we came to these actual design principles, it's really a combination of things. So if we think about, we combine kind of common tenets from wearable technology design and accessible technology design. When you kind of marry the two of those and think about how to actually build the devices, this just kind of naturally happens. So the availability, again, comes directly from wearable tech. You have this device that's on your body, it's always on, always available. There's academic research that has looked at what the benefits are of having always on or always available devices from an input standpoint. When we maintaining the silhouette really came out of kind of thinking about fashion wearables. So in conversations with experts, when we talked about wrist-worn devices, leg-worn, head-worn, we started actually looking at fashion designers who are thinking about incorporating wearable tech into their fashion shows. And when some of the most important things there were that when we add this tech, it can't impact the designer's vision. And the same thing goes for when you're buying a device off the shelf. You're often thinking about, well, when can I wear this? When can I not wear it? How visible is it versus how hidden is it? And for different people, this means different things. But for the wheelchair, that concrete scenario of if the device adds dimensionality, it will interact with the environment differently, which will fundamentally change how a person moves through space and how a person perceives space, especially when we think about the built environment and access to it. Going up and down stairs, fitting through doorways, oftentimes that will change the space. Tailoring, again, directly from the accessibility research and assistive technology literature. Adaptability, again, for tailoring, that's a principle there. And again, the familiarity comes from that dichotomous thing where you learnability for usability, and then the relationship when you're adding new devices or telling people there's a new technology. Most people will not understand what that new technology is and how it works because it's new. When you introduce it, it is still new. You have to teach people what it is and what it does, right? And then robustness is one that's pretty key. We really want to think about how these devices work out in the world and not just in the lab. So as far as other assistive technologies and devices, I think there's a lot that can benefit. Many of them, will tackle some but not all. Mounting dimensions and things are a big deal. Some of them do these things in different ways, but I think as designers, as technologies, originally this work was intended as an invitation to those folks who were for some reason intimidated by the accessibility work. But these are engineering problems at this point. If you're an engineer and you're worried about accessibility, don't worry about that. Just make it work in a wearable technology context. Don't think about the disability if that's not something you're comfortable with. There's still many of the challenges that can be solved on the design side before we introduce a device.
Any other questions? All right, going once, going twice.
Oh, one question.
Oh, there you go, Monica.
It's Monica again. Patrick, what got you involved in this charitable area of research?
So Chairables happened, I'll speak to how I got here through how I got into accessibility. So I actually started being interested in cars. So I started in looking at information. I was really interested in information and ambient information displays, ambient technologies, and intuitive UI design. And so I started as a web developer, doing a lot of work building web templates and things like that, and then getting to the end of those projects and doing compliance work to make them accessible, which always felt backwards to me. And so finding out that there is an entire field of research and an entire field of practitioners and researchers who agreed with me was what really drove me into this space of accessibility and usability in HCI. From that, I got an opportunity to do work on autonomous vehicles, thinking about interfaces in autonomous cars and what it would be like to communicate to a user. How do you communicate to a user what the car is thinking, and how do you make them comfortable when you're sitting in the driver's seat for the first time, not in control of your vehicle? And so thinking about the information exchange that happens there and what other types of information you might be able to add to it. And I went to my PhD advisor at the time and said that, you know, I'm really interested in doing this. How can we do ambient information displays in cars? And I want to know what's distracting people versus what's helpful, what's useful versus what's not. And I don't want to do it in simulation. I want to do it in a car. And basically the institutional review board said, no, you can't build a bunch of random things that flash lights and make sounds and distract people in a vehicle. It's just not appropriate. And so that got me thinking, well, how else could I do this? I learned a lot about wheelchairs over that same summer. I was in Pittsburgh, working right next door to the Human Engineering Research Lab, and saw a lot of similarities for cars as I saw for wheelchairs. And in that space, there were actually a lot more interesting problems for wheelchair users navigating space with ambient information and interactive technologies. And so it was a natural fit to kind of shift focus there. And that opened up a lot of other possibilities, thinking about sports, thinking about all the other activities that people perform in a wheelchair versus driving, which is, you know, get from point A to point B.
Oh, I see. So, a quick question is, so given that you started with vehicles and that there's a lot more machine learning, AI, adaptive devices on these platforms, it seems like what we're doing sometimes is doing two different scopes. We're collecting data like from a specific group and then kind of augmenting it on the other side. Do you see how we can kind of encourage the greater research population to take accessibility in consideration?
That is a great question and an opportunity for me to plug a very short paper that I wrote with a colleague of mine called Learning from the Front, which is really, it really gets us this idea of, if you actually think about accessibility and people with disabilities, you'll notice historically that they're often early adopters of AI and ML technologies in a very critical way. So when we think about a lot of smart technologies that are released onto the market or that get introduced, many of them offer, you know, a simple convenience. They offer a convenience factor for the vast majority of people who might use them. A smart speaker means I can now turn my lights off by just talking to this thing. But if you think about that from a disability perspective, I can now turn my lights off if I was not able to before. I can do it with my voice, what I couldn't do with my hand. And so you're actually enabling the use of that technology in a critical use scenario, which means that a person is going to be also much more critical of those applications that you're proposing, critical of the use cases, and you have to get it right. There are some things that can't be corrected after the fact in that case. So correcting speech or correcting the algorithm if it does it wrong, if the algorithm is right 60% of the time and the other 40% of the time I can correct it, or I have a means of correcting that, it's okay. But when I'm relying on this as a technology, you have to get it right. And so looking at kind of the broad range of ability of people with disabilities, first gives you both the design teams and users both buy-in and that motivation to kind of push through things that you might write off otherwise. And you avoid a lot of things down the line when you do it that way, right? If you're 95%, if you know you need to hit 95% accuracy at the beginning, you're not going to settle for 60 and then release it and then it doesn't work, failed product. So that's one aspect of it. The other one is really in, you know, just buy-in. I think awareness is a thing. So things like this, having conversations and, you know, getting people to know the variety and getting people comfortable working with these different communities is also, you know, kind of paramount in that space.
Oh, thank you.
All right, I guess we could probably end here. Thank you everybody for coming, and thank you so much, Patrick, for the great presentation. See you next time.